All right, students, so I'm going to re-record this part 3 of the video because what I posted had like my voice and delay, and it sounded like two people were speaking at the same time. It was incredibly confusing. So I'm just going to start over again. All right, so what we're going to do is work with some integrals of the hyperbolic trigonometric functions. These rules right here, you don't really have to know. These are things that I'd give you. These two right here are actually real easy to derive with basic substitution. I'm just going to show you on this. Like if you wanted to derive the formula of the hyperbolic tangent, and I think I end up sort of doing that in one of these problems anyway, but I'm going to go ahead and just do this at the side. This is worth paying attention and writing down. So let's say that we want to derive this formula. So we have the identity for hyperbolic tangent that says it's the hyperbolic sine over the hyperbolic cosine. Okay, sinh x over cos x. Well, what we could do is we could do U substitution. So we would just let U be this thing. So that would be the cos of x. We would hope that du would be the rest of the expression, and it is. Okay, remember, a derivative of a hyperbolic cosine is a hyperbolic sine without the negative, so it's a little different than it is in circular trigonometry. So actually what we have is what I got in blue. That would just be the, and I need to put my dx there. Okay, that part right there would be your du, so we're going to replace that with du. And then this part right here would be your u. So we would actually end up with an extremely easy integral to do. We'd end up with 1 over u times du. And you may recall that. I hope you do. That's the natural logarithm of u plus c. Okay? Then you just plug back in the u. So see what you would get is you would get ln of absolute value of the hyperbolic cosine plus c. Okay? Now, you might be wondering, okay, why does this formula not have the absolute value on it? It's just really unnecessary. And the reason it's unnecessary, I'll go back and let me see where my graph was. I think we kind of went through, did these graphs. Where's my, there it is. Okay, here's the graph of the hyperbolic cosine. And notice the values of the hyperbolic cosine are always positive. Okay, so what happens on that is since it's always positive, you don't have to worry about that absolute value. Okay, so that's how that goes. Now on this one, you could derive the integral of the coch the same way. The reason absolute value is on the sinh is because it's necessary based on what you would see in that graph. Okay, so anyway, those first two right there are actually very easy to derive. The sech and cosech are a little harder. So I would, give you these formulas, but I would like you to know how to derive 1 and 2. Okay, so here is a integral. This is a typical U substitution. If you have a cosh and a sinh in your integral, then it's usually nicely set up for U substitution. So what we're going to do is we're going to let U be that entire denominator. So that's going to be 1 plus the cosh of x. And then again, kind of like when I was doing this problem up here, we're kind of hoping du would just be the rest of this. And if it is, it makes this integral real easy. So du is the derivative of 1 plus cosh of x. That's 0 plus sinh of x. So that is sinh of x dx. Okay, so what we're going to do then is this part right here is going to be the u part. All right, that's what u is. And then this part right here, the sinh x dx, that's going to be your du. So everything is beautifully set up for a real basic U substitution problem then, okay? So what we'll have then is we'll have really 1 over u times du. You can think of that as du over u can be written this way then, okay? Well, again, what is the integral of 1 over u? That's the natural logarithm of absolute value of u plus c, okay? Then the last thing you do is just take the u part, which is this part, and just simply plug it back in. So the answer would be ln of 1 plus cosh of x plus c. Okay, and what would happen on this is the absolute value would not be necessary. I'd be okay if you wrote it that way. It's not wrong to write the answer this way. It's just that the graph of the hyperbolic cosine is always above the x-axis, and if you just add 1 to that graph, it's going to be a vertical shift of 1. Okay, so it's unnecessary. So we could just write this as the natural logarithm of 1 plus cosh of x plus c. Okay, and then that would be probably the best way to write the answer, but either way is right. Okay, so one thing that I like to do on some of these problems is, you have the ability to check your answer to an indefinite integral. So what do? You take the derivative of the answer, and our answer was ln 1 plus hyperbolic cosine plus c. Okay, so if we do the derivative of an ln is always 1 over that function, and then times the derivative of that function by chain rule. And you can do this in your head. I'm just going to write down what's going on the chain rule. And of course, the derivative of c would be 0. So what you would end up getting then is you would get 1 over 1 plus cosh of x, and then the derivative of this is the sinh of x. Okay, and notice that's what we started with. We had sinh of x over 1 plus cosh of x, so that's right. Okay, so it checks out beautifully on that problem. Okay, you have that ability when you're doing quizzes, exams, and stuff like that. Take an extra minute to see if you're right. Sometimes it's real easy. Sometimes, yeah, it's kind of, it's a little bit of work to check that you're right. So this is a really good example, one that's pretty easy. Okay? All right, so let's go to the next example. And what we'll do on this then is, what we know on this is we know this. We know that the integral of the cosh of x dx, we know that that's the sinh of x plus c. So what we need to do is just change this so it says cosh of u. Okay, so what we're going to do is we're going to set u equal to 2x, right? And then dx, really what's left over, we're not left over with cosh dx, we're left over with dx. Okay, so what we do, if we do the derivative, du, that would be 2 times dx. Well, we don't want dx, we want, or we don't want 2 dx, we want 1/2 dx. So there's a couple of ways to handle that. Let's see, just for variety here, we could do something like this if you want to. I usually just do this. I usually just divide both sides by 2. So I get 1/2 du is equal to dx. You could also multiply by 2 there, and outside the integral multiply by 1/2, and it would work the same way. So you can do that either way. Okay, so what I'll end up having then is I've got this. So I've got the integral of cosh of u, okay, because that's what u is, and then dx we're going to replace with 1/2 du. Okay, that's a constant that can come out of the integral, so I get 1/2 cosh, or 1/2 the integral of the cosh of u. Let me write that a little better. Okay, let's see. So we got 1/2 integral of the cosh u du. All right, so that's a breeze. Okay, the integral of the cosh is the sinh. Okay, so that would be sinh of u plus c. And then u is 2x, so that plugs back in. So what we'd end up getting is 1/2 of the sinh of 2x plus c. Okay, so that should be your solution to your problem right there. Again, that's an easy one to check. You can pretty much just do that in your head if you want to. Now, I'm going to show you a formula on this too while I'm thinking about this. This is sort of a general formula that shows up a lot. And I'm going to relate this to something you've seen before. So, for instance, you know the integral of e to the x dx is e to the x plus c. Okay, but what if we change that slightly to e to the kx dx, where k is a constant? Then it becomes 1 over k e to the kx plus c. Okay, well, on this problem, the trig functions work the same way. So we know the integral of the cosh of x dx. We know that's equal to the sinh of x plus c. But what if we change that to kx? So then if we had the integral of the cosh of kx dx, then that would be 1 over k sinh of kx plus c. Now see, that's what we did there. We got 1/2, 1 over k would be 1/2, and we have sinh of 2x. So when that pops up, you don't necessarily have to do U substitution. You can just manage it this way if you want to. Okay, so that's how that would go then. All right. Okay, so let's see. Let's go down here to example 7, and we've seen this enough with circular trig functions that we have to use an identity on this. So first of all, if we go down to this problem, there's a useful identity that we need to do. Now I'm going to go back to my formula sheet just to kind of remind you of where I got this in the notes. So way back here, I put a bunch of identities on here. So here's the one that's useful. And you will recognize this, I think, based on what you've already learned about doing the integral of sine squared x and cosine squared x. So I'm just going to take a little snapshot of that, and then we're going to use that identity to work out this integral then. Okay? All right, so where am I? Okay, so I'm here. So I'm just going to paste this on here, and then we're going to take a look at this identity, and we're going to use this identity. Okay? So, U substitution won't get you anywhere. You just need to change it to this. So what we're going to do is rewrite this then as the integral of cosh of 2x minus 1 over 2. Okay, now the way we do that is we split it up. So we're going to split this up, and I need to put my dx there. So I got cosh 2x over 2 minus 1/2 dx. And then from here, what we want to do is just split it up like this. So we would have 1/2 cosh of 2x, and that's in an integral, so we'd have the cosh dx. And then this right here would just be the integral of 1/2 times dx. Okay, so I'm just taking that 1/2 out of the integral. Like that. Why in the world did I write 2 integrals? Okay, there we go. That's a little bit better. Okay, all right, I do crazy stuff like that sometimes. Okay, so we got that. Now we're basically where we need to go with this then. And then see, we know this. See, you can use this rule now right here. So instead of doing U substitution, hey, we already did it in the last problem. So what we have is 1/2, and then you can think of this as cosh kx, so it's 1 over k, or just 1 over 2, sinh of 2x, like that. And then, of course, what's the integral of a constant? Well, that would be 1/2 x, and then plus c. Okay? Then you can go through and just kind of clean this up. So what we'd have is 1/4 times the sinh of 2x minus 1/2 x plus c would be a good way to write that integral then in its solution. All right, that's it. Okay, so you use substitution when you need to, or sometimes you use identities when you need to. And you'll get used to doing sinh squared, cosh squared, and knowing to use that identity. We've already developed some a little bit of familiarity with that. Okay, so now let me get into one where it's a definite integral. Now this one right here, this is the integral of the tang. Now if you go back to the previous page, I showed you how to derive that formula, ln cosh x plus c. So, I mean, if you have a formula given, you can certainly go ahead and just use this formula if you want to. So let's go ahead, just to save a little bit of time, and do that. So what we'll have on here is the value of the indefinite integral is ln of cosh of x, and then that gets evaluated from 0 to ln2. All right, so we're going to go ahead and evaluate a definite integral when we do this then, all right? So there's going to be a formula that we're going to have to kind of, use on this too. So now we're ready to go ahead and do this then. So let's do the theorem, the fundamental theorem, calculus. So we have ln of the cosh of ln of 2 minus the logarithm of the cosh of 0. Okay, so we got to work that out then, all right? Okay, so there's, a couple of ways to go about doing this then. So the first thing I'm going to go through and do is write this formula over here. We know that the cosh of x, by definition, is e to the x plus e to the negative x over 2. So when we do this, we're going to go ahead and use that formula, okay? So if we were doing the cosh of ln2, which we're getting ready to do here, all we would do is just plug in ln2 for x. So you would have e to the ln2 plus e to the negative ln2 all over 2. All right, so I'm going to go back in my problem and just kind of write that. Now, I still got the logarithm, but I'll have e to the ln2 plus e to the negative ln2 all over 2. And then we'll deal with that just in a few minutes here, okay? All right, and then the next thing that we'd want to work on is, we got to do the cosh of 0. So the cosh of 0, again, just plug into the definition. So that's e to the 0 plus e to the negative 0 over 2. And I'm going to go over here and just plug in. So I have natural logarithm of e to the 0 plus e to the negative 0 over 2. And there's some things that you could certainly do in your head on this when you go through this then. Okay? All right, so a little bit of background knowledge here. There's a property of logs, and you will see this a lot in Calc 2. And it goes like this. If you have a number raised to the log base b of x power, that answer turns out to be x. So an example would be something like e to the ln2, because what that means is e to the log base e of 2, so the answer is 2. And again, these things have to match. If those bases don't match, then that doesn't work. So remember, a natural logarithm's base e. So that thing right there is going to be 2, all right? So let me show you kind of what I'm going to do on this then. And you can do this a couple of different ways. Even if you look at this part of the problem right here, if you look at e to the negative ln of 2, well, you got to do this. This is really e to the negative, hold on, let me write it like this. Okay, what this really is this is e to the ln of 2 to the negative 1. Remember, that's a property of logs, that you can bring an exponent in front of a log, or you can bring a number in front of a log up to the exponent. So according to this property, that would be 2 to the negative 1, or 1/2. Okay, so what you're going to get on this then is this is 2, that will be 1/2. You can just kind of do that on scratch paper if you want. So what we'll have is ln, and then that will be 2 plus 1/2 all over 2. Okay, and by the way, your calculator would do this. I mean, I'd like students to know how to do this without a calculator, but the calculator could certainly bail you out, and if you wanted to be confident in your answer, you could just go e raised to the ln of 2, that gives 2. Or if you did e to the, even if you did, let's see if this works, negative ln2, I'm not sure if this works on this calculator or not. Yeah, it does, it's 1/2, okay? All right, so, I mean, you can verify stuff that way if you want to. Okay, then we go here, so e to the 0 is 1, so you would just have here natural logarithm of 1 plus 1 over 2, all right? So now we just got to work this out then. So, like this thing right here, if you do 2 plus 1/2, you could get a common denominator, and that's 5/2, but if you wanted to do it this way, that would be 4/2 plus 1/2, so that's 5/2, okay? So you're doing 5/2 divided by 2, all right? So I'm just going to write this as ln 5/2 all over 2, and then over here, this is going to be ln of 2 over 2, okay? And then we want to just kind of work this out, so there's a couple of ways you could do this. Now I'm going to kind of talk about how you could handle this. You can handle this a couple of different ways. That's 5/2 divided by 2, So that's 5/2 times a half. So that would be 5/4. Okay, so you'd have natural logarithm 5/4 minus natural logarithm of 1 like that. Okay, so that's one way to handle that then. Another thing that you could do, this is kind of the way I like to look at this. So if you look at this part of the problem right here, this is just a little quick arithmetic review. If you have 2 plus a half over 2, the way I like to do this is just multiply the top by 2 and the bottom by 2. It just seems easier to me. So 2 times 2 is 4, half of 2 is 1, 5 over 4. Okay, so that's how that works. All right, so the natural log of 1 is 0. So we end up with ln of 5/4. So you could end up, and I would be okay if you just gave me this answer, ln of 5/4. But there's a property of logs, remember, that says ln of a fraction. Log of a fraction is just the log of the top divided by the log of the bottom. So that's probably the most likely way to see that answer. To me, there's not a thing wrong with writing the answer just as ln 5/4. I don't know about my math lab, though. You know, it's a computer program. So either one of those is okay. All right, now I want to mention on here that what we can do is we can check our answer on this. So I'm going to just kind of show you what a couple of things you can do on this. I've got a couple of things put here already. So remember, you can do this, and this will really help you on your exams. You're doing a definite integral, so you can tell you're right. Okay, so if you go all the way back to the beginning and the tangent, and let me review where this is. You're going to find a catalog button. Where in the heck is the catalog button on? There it is, right there. Okay, so this is the only place where I know where the hyperbolic functions are. So if you went second catalog, now you would have to scroll down, way down to the bottom until you found the hyperbolic tangent. Okay, and you're just as well to put it in this way instead of putting in the definition of the hyperbolic tangent. So it's in here. Got a good calculator. All of the hyperbolic trig functions are in here. Okay, come on. We ought to be there. S. We ought to be there in just a second. Takes a while. There's a lot of junk in this calculator. Holy cow. All right, so let's see. There's the tangent. So I'm going to put in tangent of x. And when you're graphing trig functions, make sure you're in radian mode. Okay, I'm glad I checked. Okay, so I want to make sure that I am in radian mode. And then we'll set up a window. Let's see, we're just doing the integral from 0 to ln of 2. So what you could do on this is, you can do this. Let's see, if you do ln of 2 is 0.69. So why don't we just do this, and this will be good enough. For a window, let's go 0 to 1. Scale by whatever. I'll scale by 0.5. For the y's, let's just go like 0 to 2 or something like that. Okay, I've kind of got this on here too. You can do this window here if you wanted to. So if I graph that, I've got a function that looks like that. Then, like I've taught you, you can go second trace, option 7. The lower limit of our integral was 0. The upper limit of our integral was ln of 2. So it'll shade that in, and then it'll give this answer. So 0.69 would be that. And then just take the answer we got. So the answer we got was ln of 5 minus ln of 4. And you get, what in the heck did I do there? Oh, there it is. I said I'm looking at the wrong thing, okay? This is the answer right here. Okay, I'm kind of freaking out here, all right? So notice this, that's the answer right there. Okay, that's the answer to the integral, so is that. So see, those two things match up, so that means you have the right answer, okay? Okay, so those problems aren't too bad. I mean, some of the integrals on hyperbolic trig functions, or most of the ones we're going to do are going to be straightforward use of identities or U substitution, because we haven't really even got to the point yet in this class. We don't do that until Chapter 8, where we start looking at lots of new integration techniques, like integration by parts and so forth. Okay, so that will wrap this up. I'll post this, and hopefully this will be more understandable with just one voice instead of two. All right, good luck.